Okay, let's just dive right in. Every single day, it feels like AI is doing something new and incredible, right? It's writing poetry, it's discovering medicines, it's creating art that's just, wow. It's so easy to look at all that and think its potential is infinite. But what if I told you there are fundamental, totally unbreakable rules that govern what AI can learn, and more importantly, what it can never learn?
And yeah, that is the big question for this entire explainer. We are not talking about today's technology being a little too slow or not having enough data. No, we're talking about problems that are provably, logically impossible for any computer or any AI to ever solve, no matter how powerful it gets. So this first barrier is probably the most mind-bending one. It's the idea of the uncomputable. And this isn't a hardware problem, something we can fix with a better chip. It is a fundamental limit that's baked right into the laws of logic itself. Think of it like this. It's the computational version of trying to draw a square circle. It just can't be done. To really get this, we have to go all the way back to the legendary work of Alan Turing. I mean, long before anyone was even thinking about the AI we have today, he was asking this really simple but incredibly deep question. What are the absolute limits of what a machine can compute? And that question laid the groundwork for, well, everything. Okay, so here's a famous logical trap that proves this point. First, just imagine we have a perfect program. Let's call it Checker. Its only job is to look at any other program and predict with 100% accuracy if it will finish its task or just get stuck in an infinite loop. Sounds useful, right? Well, now we create a second kind of mischievous program called Paradox. And Paradox is designed to do the exact opposite of whatever Checker predicts. You see the trap? If Checker says Paradox will finish, Paradox is programmed to loop forever. But if Checker says Paradox will loop forever, it's programmed to immediately stop. It's a contradiction. No matter what Checker says, it will be wrong, which proves that a perfect program like Checker can't possibly exist.
And that little puzzle, that's known as the halting problem. And it's not just some clever brain teaser. It is the bedrock proof that some problems are what we call undecidable. That means there is no algorithm, no computational solution that can ever exist for them. Period.
So this all brings us to a really crisp, clear definition. A problem is computable if you can write an algorithm that is absolutely guaranteed to solve it in a finite amount of time. But if no such algorithm can ever possibly exist, like with our halting problem, then the problem is uncomputable, forever.
All right, so some problems are just logically impossible. Got it? But what about the ones that are technically possible to solve, but would literally take longer than the age of the universe to figure out? Well, that brings us to our second huge limit, the intractable.
Let me ask you a question that seems simple but has massive implications. Think about a really hard Sudoku puzzle. It could take you hours, just agonizing over where the numbers go, trying to find the solution. But if I hand you a completed puzzle, how long does it take you to check if it's correct? Seconds, right? It's super easy to check. This huge difference between finding a solution and checking one is at the absolute heart of one of the biggest questions in all of computer science.
This leads us right to the famous P versus NP problem. So, P problems are the ones that are easy for a computer to both solve and check. Think sorting a list of names. Simple. NP problems, on the other hand, are the ones that are really hard to solve, but, just like that Sudoku puzzle, they're easy to check. Imagine trying to create the perfect seating chart for a huge wedding with 1,000 guests, where you have to make sure no one sits next to someone they dislike. Finding the solution would mean trying out a bajillion combinations, which could take a computer billions of years. But checking a finished chart to see if it works? Easy.
Now, the billion-dollar question, and I mean that literally, there's a huge cash prize for whoever solves it, is whether P actually equals NP. Are all those hard-to-solve NP problems only hard because we just haven't been clever enough to find an easy shortcut yet? Most computer scientists think that P does not equal NP, and if they're right, it means some problems are just fundamentally intractably hard. For AI, that means some learning tasks, even if they're not impossible, might as well be.
And this whole P versus NP thing connects to a really deep idea about mathematical proofs. See, if P did equal NP, it would mean that for any true statement, there would be a short, easy-to-find proof for it. And since finding proofs for things is often incredibly hard, discovering some kind of easy way to do it would completely change science and AI as we know it.
So, given these enormous boundaries,
the things that are completely impossible and the things that are practically impossible, how do scientists even begin to study machine learning in a serious, rigorous way? Well, it turns out they created a formal rulebook.
That scientific field is called computational learning theory, or COLT for short, and you can basically think of it as the official science of learning from data. It gives researchers the actual tools they need to ask really precise questions about what can be learned efficiently and, just as importantly, reliably.
And this toolkit has a few key ideas. The one you really need to know is polynomial time learnability. That's the gold standard. It basically asks, can a concept be learned in a reasonable amount of time without taking, billions of years? The theory also gives us ways to measure a problem's complexity, which helps scientists figure out just how much data an AI is going to need to learn something without making a ton of mistakes.
And by using this toolkit, scientists can actually prove whether certain types of problems are learnable or not. It's not guesswork. For example, the source material points out that a relatively simple concept, like an AI learning to identify a pattern of overlapping rectangles, is proven to be efficiently learnable. But as soon as you get to more general geometric shapes, it gets way, way harder, and there are actual proofs that set a lower bound on how fast any algorithm can possibly learn them.
Okay, so I know we've talked about uncomputable paradoxes and problems that take forever to solve. This might all seem really abstract and theoretical, but I promise you, understanding these limits is incredibly important for the real world of AI that we see every day. At the end of the day, this theory is the ultimate reality check for all the AI hype out there. By understanding what's impossible or what's intractable, researchers can stop wasting time and instead focus their amazing energy on the problems we can actually solve. It's this theoretical foundation that gives us confidence in the reliability of really critical AI systems, from the ones that help diagnose diseases to the ones that design our bridges. And this, for me, is the most important takeaway of all. These limits, they're not failures of our engineering or a sign that AI isn't good enough. They are the fundamental rules of the computational universe. They're like the laws of physics. And knowing that AI researchers are achieving all these incredible things while playing by these incredibly strict rules, well, that just makes what they're accomplishing all the more astounding.
So the next time you see some crazy new AI breakthrough, just remember the invisible boundaries it's operating in. The real magic isn't about trying to build some all-knowing machine that can break the laws of logic. The real genius lies in finding new, creative, and powerful ways to solve meaningful problems, right inside those lines.